Okay. So, so we have this Clifford module bundles, and so we discussed this sort of generalized Dirac operators. So this generalized, you will realize why we call it generalized Dirac operators. It's not the Dirac operator, it's one of those more general types of operators which are close to Dirac operators. Okay, so the setting was like this. We had M was a Riemannian manifold. So metric was important. And then you remember we formed the Clifford bundle. I mean, Clifford algebra bundle, I should say. So this, we can just say, I mean, Clifford algebra, we form Clifford algebra of, say, the tangent bundle at each point. It's a vector space with this inner product, positive definite inner product. We can take Clifford algebra, and then at each point we did that, and then this is a bundle of algebras. So it's a bundle of algebras, right? Okay, finite dimensional algebras actually. Algebras, I mean, it's a vector bundle, right? Yeah. Over M. So then let S over M be a complex vector bundle such that at each point, the fiber of S at X is a module for Cliff, such that for any X belonging to M, this S sub X is a Cliff TMX module. Right? So this, in other words, this acts on this. So at each point we have this. I mean, you can express module notion in different ways. But for example, you can say this cross Sx goes to Sx over X. And then now we are going, so we fix the connection. Yes. And then using this, we defined the Dirac operator, D from, so or generalized Dirac operator, I should say, D from C infinity of S to C infinity of S. And in local coordinates, we described it as D equal to some, say, E alpha times nabla E alpha. So this E alpha is an orthonormal. Yeah, it's an orthonormal frame. Right. For Tm, of course. I mean, this is local, right? Because globally it need not exist, but locally it exists, and we check that this is well defined. And okay. By the way, some more terminology. S can be called generalized spinors. So S is again, generalized. I mean, this is a kind of risky, dangerous notation on terminology, spinor bundle. It's not really the spin bundle or bundle of spinors over n, because that cannot be defined in general. But because we call this generalized Dirac, it makes sense to think of it as generalized as spinors, and notation S kind of suggests that. I mean, this is really generalized. It's not the spinor bundle. We will see that soon, but that's not the one. Okay, now today we are going to impose some more structure on this S. So impose more structure on S. I would say more structure and conditions on S. Basically, the reason for this is that we want this Dirac operator to be a self-adjoint operator. So this will guarantee that. Yeah. So this is to make sure D is self-adjoint in some sense. So that's important thing we want to have. So this condition is that, first of all, we want S to have a Hermitian metric. A Hermitian metric on S. Not only that, we want this also to be compatible with the connection. Compatible with its connection nabla. Okay, so that's one condition. And the second condition is that we want this connection nabla on S to be compatible with Levi-Civita connection on T. Connection oh, yeah, by the way, yeah, I should say a little more, but such that also, then there are two such that, yeah. This Clifford action we want to be a skew adjoint, that's important, yes. Such that Clifford action on S is skew adjoint. So this skew adjoint means C acting on S1, S2 plus S1 CS2 equal to 0 for all C belonging TMX for all X, right? So because Clifford algebra acts, it means that also tangent vectors also act as operators on S, and we want these operators to be skew adjoint. If there was minus sign here, it would be self-adjoint, but we want it to be skew adjoint. That's one condition, part of the package one. Now, condition two is that the connection on S wants to be compatible with connection. So my notation is, yeah, the Levi-Civita connection so I just put nabla Levi-Civita and C on TM is compatible with connection nabla on S. So what does this mean? This has to be defined. This is not a self-explanatory concept. It has to be defined. And the definition again is like this. So let me write it here. So we want this to satisfy this condition, nabla. So for any vector fields x and y on M, and for any section of S, we want to have this relation that nabla, you see ys. You see this vector field using Clifford multiplication on S, acts on S, gives us a section of S again, and you can take covariant derivative with respect to X. So this should be equal to, this kind of Leibniz rule is satisfied here. Obviously, then here we have nabla Levi-Civita of Yx times S, this vector field again acting on S, plus Y, this vector field times acting on this section. See? This is the connection on S. This is also connection on S. I mean, this is like here maybe, yeah, okay, so. But this is the Levi-Civita connection. So this is kind of Leibniz rule, but you have to use Levi-Civita connection in this component. In this sense, we say that this is really a Clifford module 1. So S is inner product nabla satisfying this above condition is called the Clifford module bundle. So it's a kind of enhanced notation. This is what we need. As I said, the use of these conditions 1 and 2 is to make sure that this operator Dirac that we define is a self-adjoint operator in the sense that I'm going to define. Okay, so this is all we need now. The first thing we need to do is to compute square of the Dirac operator. So computing E squared. Okay, so we need a concept, which is the concept of synchronous frame. So what is a synchronous frame? So local frame E alpha is called synchronous if satisfy the following condition that nabla E say beta alpha at M is equal to 0, and the commutator of these two things is also 0 at M. At M is equal to 0. Yeah, so I should say synchronous frame at n. You see, so you have your manifold, and you fix a point M. So this point M for the discussion is fixed right now, right? And we say that the framing is synchronous with respect to M, or synchronous at n, if this condition and that condition is satisfied. So, yeah, I mean, this is just at n, right? It's not that globally or even locally this is equal to 0, or locally that is equal to 0. No, just at n, we want this to be true. And now the point is that synchronous frames always exist. So the fact, which I won't prove, you have to use a little bit of differential equation to show that for any n, a synchronous frame at n exists. I mean, you have a lot of freedom in choosing the frame. Among those many possible frames around m, there are many that satisfy this sort of condition at m. And so the word synchronous, I think, comes from general relativity, and we don't need to know its exact meaning. So pick a synchronous frame then. Pick such a frame M, and then let us compute d2 of s. Then we just want to compute d2 of s. So what is d2 of s? Let's compute it at n again. S is a local section, and this is, so this is equal to, sum alpha beta e beta nabla e alpha, or nabla beta. I just write nabla beta e alpha nabla alpha s. I mean, this is, remember, this is d of s, right, as our definition. And then again, this is, you apply the same operator again, so you get d squared of s. And of course, we have to evaluate this at n. Now we can use Leibniz rule here and compatibility of the connection to compute that this is equal to basically sum alpha beta e alpha nabla beta nabla alpha s. I mean, everything is at m, right? So this component nabla beta e alpha drops because at m this is equal to 0. So this part only remains. So the second order operator remains.
Sorry, what do you mean by m equals to 0 on your equation there?
M?
Yeah.
M is a point on the manifold.
Yeah. So on your equation there, it says evaluate at m is equal to 0 on the right hand side.
This is
right hand side.
At m, this is equal to 0. Yes, that's the condition.
It's on the right hand side, the equation for d squared x, d2s.
Yeah, that's also at m. I want to know what is the value at m. Yeah.
And then equals to it, and you write an equation, then it says at m is equal to 0.
That's, right, at m. Yes. Thank you. Yes. Is that your question?
Yeah.
Yeah, okay, exactly. Yeah, that's just n, right. Thanks. Yeah, very good. So now we just separate it in two parts. Sum over alpha equal to beta, and then alpha different from beta, which has two parts. So this becomes, so remember E beta squared is equal to minus identity. So this becomes equal to minus sum, you see, nabla beta nabla alpha squared S over alpha. If you put up beta equal to alpha, you get that term. It's -1 because this is our convention for Clifford algebra, and -1 acts by minus identity, so this is this operator. And then plus sum on beta less than alpha. We can just, okay, so we can just separate these two things. Just write nabla beta, nabla alpha minus nabla alpha, nabla beta, and then S. Okay? So you see off diagonal terms, two parts, up and down, and then we can just write it in terms of, say, up terms, and then we just use the fact that E alpha, E beta plus E beta, E alpha is equal to 0 for beta different from alpha, right? We just use this, we can write it. And this term now, of course, reminds you of curvature, right? So this should remind you of curvature. Indeed, this is a curvature term. So it looks like now we are able to write d squared of S at this point as sum of the squares of these things. And so let us explain those terms a little bit. Okay, so we can just write it as, so let's call this term 1 and 2. So we can just write it as 1 plus 2. 1 refers to this term. You see, 1 differentiates twice. It's a second order differential operator. But this one, it's a kind of strange operator. It's a curvature operator, which is not differentiation after all. Although we have differentiated twice and subtracted, but the end result, it looks like it's not, we are not differentiating. Although we are differentiating, but this is not a differential operator. This is a tensorial object. So this we call it the second part. So this is exactly the curvature term. We call it 2. So 1 plus 2. So 1 is a kind of Laplacian, but it's not quite Laplacian. We'll see. Now,
sorry, isn't 2 just 0 by our assumption of it being a synchronous frame?
2? Not just at M, but we just keep it. At M, it could be 0. What was the condition that I have?
Well, we have the bracket of nabla, alpha, nabla, beta at M is 0.
I mean, yeah, that's at M, but I want to keep it because away from M, this will not be 0. So I want, you see, there is some argument here now to be made. I am looking at this thing at M, but I know that I have only chosen one frame and I'm checking on one frame. But this expression has a global meaning, so I keep it. And then I argue that, okay, in that frame, this is 0, but in general, I'm going to keep it away from that frame. So there is a rather subtle argument, and this happens in differential geometry quite a bit. When you go into special frames or special coordinates to prove things, at the end, we have to make sure that the result that you get is independent of choice of coordinates. So, yeah, okay. So, are you okay with my explanation?
I think so, but didn't we also use? But we did use a fact about synchronous frames earlier on, but the fact we're doing it at M.
We use the thing about synchronous frames, but at the end, I want to find an expression for d squared, which is meaningful, is independent of choice of frames. So I just keep it like that.
But what I mean is that in the derivation of this, we did use the fact that nabla beta of E alpha is 0 to derive this. So surely this wouldn't
Oh, yeah, yeah.
be valid outside of M.
Yes, but I'm going to argue, so, right. So I'm going to keep that and argue that the expression is well defined, and then I give this to you as the identity, and to check that, I say, okay, go to this frame and check it, then it's okay. You know what I mean?
I think so.
Yeah, I mean, it's a very important point here. Indeed, we have to pause and think. I am just deriving an expression, and I want to just keep going. I will find a formula at the end, and I tell you that d squared is equal to that, and then I say, okay, if you want to check that, start the argument from beginning again. So there is some subtlety in this type of argument. So I'm not done yet. So I keep going now. So just watch. Yeah.
Okay, thank you.
Yeah, yeah. I mean, no, that's you raised a very good point, Tori. Thank you. Yeah. 2 is a kind of is a curvature term. Indeed, this expression by itself is not well defined. So we have to make sure that nabla. So let nabla alpha, nabla beta, nabla alpha minus nabla alpha, nabla beta equal to k beta alpha. So this is an endomorphism valued so please endomorphism of S for all alpha and beta. So now let K. So here is the definition. So define K, some E beta, E alpha, K beta alpha. So this is an object that's well defined. So is a globally defined endomorphism of S. So now we are going to, we are not done, so I have to make sure to replace this by a good meaningful term. So we will do it this way. So I'm going to keep it like this because I need.
Can I ask a quick question?
Yes.
So that number 2 term you have there, is there no E alpha, E beta appearing in that sum? Where did they go? I don't understand.
Oh, there is this E alpha and E beta.
Because you use the anti-commutativity to get the commutator of the nabla, right?
Yes. I should have them. Yeah, I should have them. I think I'm going to put this to be. No, I have it. E beta, E alpha. No, I have this. Yeah, I should have this here. E beta.
Okay. Okay, right. Okay. And when you say the curvature is an endomorphism of S, what do you mean by that?
Right. So the curvature of a connection, we saw that is an endomorphism value 2 form, right? So if you fix the value of indices, like tangential indices, this alpha and beta are tangential indices. For any pair of indices, this connection, like K alpha beta or Kij or Rij, we use R. It's a matrix, right? It's a matrix which is an endomorphism of the fiber at that point. So this is an endomorphism value, I think. So this is the idea of curvature of a vector bundle, right? That we discussed some time ago, right?
Right. I thought it was an endomorphism of the C infinity of S. So I was just a little confused.
Endomorphism of C infinity of S. Well, you can always work in module context or the bundle context. I mean, if you are more algebraically oriented, you can think of modules. But if you are more geometric oriented, you can think of bundles. But you can formulate it in both ways.
Oh, okay, got it.
So there are two parallel languages, geometric and algebraic languages. Right. Is that okay now? So now, so this is this term. Now, let us define this operator also, which is the second one I want to define. Consider the operator. Now I'm going to replace this by something meaningful, which is nabla star nabla, where remember this connection nabla goes from C infinity of S to omega 1, which is, I think Jeremy likes it. I just put it like this, omega 1 tensor C infinity of M over C infinity of S. This is our connection, right? So there is an inner product here on S. I mean, there is also an inner product on here, an inner product on here. And conceivably, so this is nabla, let me put it like this. And conceivably, you can take the adjoint of this operator. I call it nabla star. Now, you have to make sure that the adjoint exists. You can read the proof in Rowe's book or in the other reference I gave you. So this nabla star, formal adjoint of nabla. Okay, so this operator is globally defined. I mean, to define this operator, I don't need any synchronous frames, any special frames. I globally defined it. There is this nabla, originally defined globally like that. And this nabla star is the formal adjoint. Now, of course, you have to show that the formal adjoint exists. This can be done. Once you do that, then you have this operator. Okay, so now this operator is equal to that only in a synchronous frame, but this operator is well defined. Now I claim that I have proved this Weizenburg formula. So let me write it here now. So the corollary, corollary is this so-called, now this has a name, so it's called Schrödinger I don't know, Weizenburg Vishnerovich Wagner, maybe one more name, but I don't know. But certainly Schrödinger was the first who thought about these issues, because he thought about Dirac operator on curved spaces, and he was wondering what is this squared, and he came up with similar terms in a more limited context, but basically he had the right idea. So Schrödinger is correct. Weizenburg, I believe, also thought about it. I believe Lishnerovich had the more general case, and Bachner also had some special cases. So all these guys deserve to be mentioned. Formula. So this now, the formula is that indeed, so let me erase this part, is that indeed d squared of S is equal to nabla star, nabla S plus Ks. In fact, you can just write it, this is better to say d squared equal to nabla star, nabla plus K. That's the formula. So vis-a-vis the issue that Tori mentioned, I mean, you see now, I have a well-defined, of course, d squared is well-defined, d is well-defined. This operator is well-defined because it's globally defined. This operator is also curvature operator of the bundle, so this is also globally defined. Now, this is the claim. To prove this claim, you go to this synchronous frame and check it, and because it's a tensorial, because both sides are true in any frames if they are true in one frame. And for that purpose, you just use the synchronous frame at M, because M is arbitrary, then it's true. So this is a kind of technique that you use in differential geometry very often. That's very important. So that's. Now you have to check that this corresponds to this one. If you use a synchronous frame, and that term corresponds to this one in the synchronous frame. So I like now to see if what you think. Any questions?
Well, maybe one, and maybe I'm probably just misunderstanding this, but if we can find frames, so if for any point we can find a frame such that this kappa is 0, that feels weird if you have a bundle that's curved. How can you?
No. I did not say that thing is, this is, I did not define kappa. Okay, so I'm not, I mean, kappa, I'm defining it to be, so the definition of kappa, the definition of K or kappa is okay, right?
Yeah.
We don't have any issue. Now, we are looking at d squared. We say that d squared is equal to this. Now, okay, so, okay.
So I guess to more clearly state my question, it feels weird to me that since it looks like kappa encodes some invariant, some well-defined property of your bundle,
Yes.
it seems weird that we can find a frame in which it's 0 at any point. So that we can pick a point and a frame in which kappa is 0. Because that feels weird to me. But
Yeah. No. Yes, to me too. I'm trying to give the sense of logic of this argument. Yeah, I mean, it's a kind of, it's a tricky argument. I mean, you're really like going on a very kind of thin thread here. So let me, but okay, so yeah, I totally agree with you. I mean, I have to, we just wrote this identity, I mean, for d squared computing in one coordinate chart. Um, yeah, the thing is, this operator, I'm also getting worried about this E beta E alpha because I don't have it in my notes, but I have to put, okay, why don't we, yes, yes. I don't have this in my notes, so I have to. Yeah, maybe we have to use some compatibility with, no, I don't think we use compatibility in this case. Yeah, okay, so let me think about it over the break. Yeah, no, okay, so this is not done yet. Okay, so I owe you this, okay. Only half done, okay. Okay, so we're gonna do it a little later, yeah. But the formula is, it's a Weizenburg formula or dictionary which shows you a formula. This is the correct formula. And to prove it, you really have to go into special coordinates. So, okay, very good. Yeah, so yes, so this I will give you. I'm a bit worried about existence or non-existence of this here. I'm not sure I have to put this. It could be related to resolving the issue. So, right.
Is there a formula for the adjoint of the connection?
There is a formula, yes. There is a formula. I mean, it can be obtained algebraically. In a special coordinates is exactly given by what we have.
Okay.
Yeah, this you can read in Rowe's book or Lawson also. Right. So now this relation, the applications of this is there is a so a corollary of this Weizenburg is right. Okay, so all right. So now, okay. Okay, so I'm wondering if we should do it now or no. Maybe I'll do this a little later because I want to make sure that they get this proof right and then we can check it. Right. So now next thing is to do, independent of this anyhow, is that this proposition B from C infinity of S to C infinity of S is formally self-adjoint. So this means inner product of D S1 S2 is inner product of S1 D S2 for all smooth sections of S. Okay. I mean, there is a, you remember there is a I mean, inner product on S, there's a Hermitian metric on S. So you can do fiber-wise product, and then we can use the volume form, assuming N is compact, or we just work with compact support sections. At least one of them is compact support, then this makes sense, and we are saying this is equal. This is why I just say formally self-adjoint. Self-adjoint unbounded operator like this is more technical definition, which we don't need right now. Okay, so proof. Again, we have to compute in a synchronous frame. Again, choose a synchronous frame. Now, actually, right. Okay, now actually, before doing that, let me say it this way. So let's call this a star. So let me say this, that to prove a star suffices to show that I use curly bracket now, D S1 S2 minus S1 D S2 is a divergence term. So what does this mean? This is a basically a function. You see, look at this. This is a function on n. This is a function on n. Why? Because we are just doing fiber-wise product of this section and that section. We use curly bracket for this. And remember, the inner product of these two things was equal to integral of this fiber-wise, and then we integrated against volume form, right? And provided M is compact, or these guys, one of these guys have compact support, for example, or could decay. This is a form, and this. Now, if this term is divergence of some vector field x, right? If, for example, divergence of some vector field x, then this Stokes formula shows that this is equal to 0, right? Then by Stokes divergence theorem, really, then you get that actually this is equal to 0. So to check that this is equal to that, we will show that the difference, because this term is really obtained by integrating this curly bracket. So we just show that this is a divergence term. So that's a common technique again. So that's the explanation. We don't need it. This is the idea. So how to show that this is a divergence term? That's tricky. So again, we want to show that this is the divergence of a vector field, right? So we will construct a vector field, but to check that, we go to synchronous frame at each point. So choose now, okay, I can say choose a synchronous frame. At M. So now then we can just say, okay, so then DS1 S2 minus S1 DS2. So this is equal to sum over alpha. Just use the definition of DS1, which is E alpha nabla alpha
I mean, this is for this one, nabla alpha S1 and S2 minus S1 E alpha nabla alpha S2. Yes, okay, so this is just definition of D, operator D. Now I can use the compatibility property, bring this to the other side. So I can just say that this is equal to, just say that, okay, so that's equal to sum over alpha. I don't touch the first one, E alpha, alpha S1, S2, then switch sides, E alpha S1, and nabla alpha S alpha, I mean S2, sorry. You see, I said that the Clifford action is a skew adjoint, so I can move this to other side, changing sign, because Clifford action of vectors is a skew adjoint. So this is this one. Okay. And now I use compatibility, which is, so here, this is, I use property 1 of the first of the lecture, and now I use property 2. So that's equal to sum over alpha. Then I've got nabla alpha of E alpha S1 and S2. I don't even need these extra brackets, so that's this thing. So now this is equal to D star of omega. This is D star of omega. For the one form, omega defined as defined by, so omega of x is equal to minus x acting on S1 and S2. Remember this D star, I mean, decreases the degree of form by 1. So it goes, for example, from omega 1m to omega 0m. So we are saying that this function is equal to this function, but this function is not any other function. It's the star of a one form, and this one form is given by this formula. So this needs to be checked. So I just leave this as an exercise. I mean, working with this star needs a little bit of preparation, but this is very standard. So this is exercise. And okay, so this is a divergence term. So is a divergence term. As I said, now you have to use the Stokes formula to make sure that. So now this is trivial. Stokes formula implies that integral over m, the star of omega times the volume of m is equal to 0. This is divergence formula in this case. It's a divergence term. So this is okay. So this I just write it as an exercise again. Remember, Stokes was integral d omega over m is equal to integral of omega over boundary of m, but basically. All right. I mean, so let me give you the hint here. Integral d omega over m is equal to integral of omega over boundary of m.
But here, basically, this is equal to 0. So this term is missing. So this is equal to 0 for any omega with compact support. So you have to go from here to there. You can use it. You can do it. Okay. So this will prove self-adjoinance. Remember, we used both properties of compatibility, property 1 and 2 of compatibility to prove formal self-adjoinance of Dirac operator. Now, okay, so basically this is the kind of prototype of operator we want to compute its index. So we'll discuss. Any questions?
Where are we using this assumption of compatibility with the Levi-Civita connection?
Compatibility with Levi-Civita connection?
That was one of the assumptions we had, right, at the beginning. Where are we using that in these proofs?
In these proofs? Well, it's possible that in proof of computing this squared, we used it. It's possible that.
Oh, right, okay.
It's quite possible because that proof is not complete yet. But I think that part of it, I think it's quite possible. Okay, so we'll go back to that issue. But here we used 2 properties anyhow.
Mm-hmm. Okay.
So let me stop the video. I mean, pause the video. So some examples. So we want to construct now examples of these Clifford module bundles. So we need an algebraic fact first that you see the Cliff or the algebra of a vector space is actually, I mean, inner product space is actually isomorphic to exterior algebra of V. I mean, this is a linearized morphism. So there exists canonical, I'm saying, linear isomorphism. I mean, not algebra isomorphism, but a linear isomorphism. And the only way to prove this canonical linear isomorphism is to fix an orthonormal basis. So proof, pick an orthonormal maybe has to be oriented as well. So let me put it here as a question. Perhaps orientation is needed. Oriented basis for V, right? So we have this E alpha beta is equal to delta alpha beta, and so on. So then elements here, Cliff, you can write them. This guy's EI1 dot EI2 dot EIK, mean for all I1 less than I2 less than IK less than equal to n bigger than equal to 1. These objects the linear basis for Cliff, as we saw many times before. And also, similarly, EI1 wedge EI2 wedge EIK for the same set of indices is also a linear basis for wedge V. I mean, wedge V, of course, is just direct sum of wedge KV, K from 0 up to dimension of V, right? And now linear isomorphism is just by sending, so define. You just send these things, EI1 dot EIK to, EI1 veg EIK for all cases, right? So, I mean, the fact that these two vector spaces are isomorphic as vector spaces, it's not surprising because they have the same dimension. And dimension is the only linear invariant for vector spaces. But the point is that this is a canonical. So there is something to be checked here, okay? So and that's an exercise. It's very important actually to check that this isomorphism is independent of choice of orthonormal basis. Maybe orientation is needed. So check, because I need this fact right away. Check star. This isomorphism star is independent of choice of orthonormal basis. In other words, if you pick another orthonormal basis, then you get exactly the same linear isomorphism. You don't get a different. So that's the point. Okay, so this is a basic algebraic fact. Now, pure linear algebra, in other words. So now we are going to use it over manifolds. So, this bundle, the Clifford bundle, Clifford algebra bundle, Tm is also linearly isomorphic to veg Tm. And I just use this isomorphism with veg T star of it. Here I just use duality obtained from inner product. Okay, so inner product that we discussed last time. Inner product duality. Okay, so then of course smooth sections of this are nothing but differential forms, right? So C infinity of veg of T star of m is equal to Dirac sum of omega Pm, right? P bigger than or equal to 0. So then this guy, this bundle, so I can take this as my S. Okay, so I take these objects as my S, and now what is the modular structure? So what is this action, Clifford action? I'm not sure what we use. Did we use Cliff TM for bundle or smooth section? So there is this confusion all the time, but that's okay. So whatever you want to choose, I just use it as, I can put C infinity if I need it, but that's okay. Cross S to S. So this is called Clifford action. But how is it defined? I just argued that this S is isomorphic to the Clifford algebra itself. But you know that Clifford algebra is a module over itself. Like any algebra is a module over itself. And you can transfer that structure using this linear isomorphism. So the rest is easy now. But you have to think about it. So I'm saying since any algebra A is a module
over A, I mean, n equal to A is a module over A. So this cliff module structure on cliff Tm. I mean, this is the bundle version of this purely algebraic factor, that's obvious, Tm. Can be transferred by using this linearized morphism that I just raised to a bundle. Gives us this. Okay. So this is our first example. So in other words, differential forms. I mean, all of them, you need all of them, right? Omega P of n, P bigger than or equal to 0, is a Clifford module bundle. Clifford module bundle. This is true for any Riemannian manifold, in other words, I'm saying, right? So this is true for any Riemannian manifold. So this is our example. And of course, you can put, you can define using connection, using the Vicevita connection on Tm, and you get a connection by duality. You get a connection on T star of n, okay, and then you can get a connection in the canonical way on all tensor powers on exterior powers on which P star of m. So there is a connection, nabla, in a natural way on this big space of differential forms. And also there exists inner product that we already used. And all these structures are compatible in the sense that I defined. All compatible. Okay, there is a lot of details to be checked, but this is done, so all compatible as specified. Okay, so this is really a Clifford module bundle with compatible metric and compatible connection, and everything is okay. So the question now is, what is the Dirac operator? So that's the question. So the question is really, what is this D from Dirac sum omega P of n, P bigger than or equal to 0 to Dirac sum omega P of P bigger than. So because, well, I mean, in general, for any module bundle, there's a Dirac operator. So the question is, what is the Dirac operator in this case? So this Dirac operator is a very well-known operator. Basically, our first Dirac operator on curved, generalized Dirac operator. So let me put it like this: generalized Dirac operator. And the computation, so let me put it like this: computation shows.
Could you explain the Clifford module bundle on the differential forms?
Can you speak a bit louder, please?
Yeah, can you actually explain the Clifford module bundle on the differential forms of it? I'm not exactly sure if I get it.
Okay, so you mean this one? Yeah.
Basically.
Yeah. Okay, so I mean here, as I said, this is by transfer of a structure. You see, any algebra is a module over itself. So Clifford algebra is a module over Clifford algebra.
Yes.
Okay, so now, but now we know that Clifford algebra is isomorphic to wedge T star of M.
Yes.
So we just, so in other words, I'm saying A cross M to M. This is your module action. I just replace this by M prime by using an linear isomorphism, then I define it. This is called transfer of a structure, right?
Yeah, but then that gives you a module on S, but the differential form is smooth section of S.
Oh yeah, this is again an issue of Jeremy. I mean, if you define, yeah, so okay, so it's really fiber-wise a module. That's we really want to be fiber-wise modules.
Oh.
No. I mean, wait. I mean, don't agree too quickly. What I'm saying is this: if you have a fiber-wise module, then sections also become modules. Because if you have a section, you can fiber-wise act, and then you get a new section again, right?
Yeah. So at each fiber, it is actually different.
Yeah. It's yes, exactly. It's like a family of these modules. Yeah.
Oh yes.
So the picture is there's a quite a geometric picture. Is that there's a family of these modules, point-wise or fiber-wise, changing it.
Yeah.
If you want, you can then take sections. Then you get a big algebra of sections, a big algebra of the sections of the module, and then not big algebra, big vector space of sections of module. So you have these two pictures again, but you can work. Yeah. Okay. So.
But then also you also say that this C star of S is equal to the direct sum of something. It's equal to direct sum of the direct sum of these P forms. But this direct sum
HP of T star of M. So the module is really, yes, direct sum. Actually, yeah. I mean, this is the I mean, this wedge P this is your big module if you want. So that this smooth sections is just that one.
I guess you also would want to say you use the fact that the smooth section of direct sum is equal to direct sum of smooth section.
Yes, that's more or less by definition. Yes.
But then also this direct sum of forms is also an algebra over the smooth, like it is an algebra itself over the smooth map.
Yes, it is an algebra over that. Yes.
I was just slightly confused if it is that one or if it's the one that you were saying the fiber-wise, but I guess it is easier to understand it as fiber-wise thing.
Yeah. The fiber-wise picture, I think the fiber-wise picture is a kind of more geometric and better, but sometimes we have to use algebraic picture. And again, maybe at some place not completely consistent with the notation, because this Cliff TM, I'm not sure what did we use for this. Is this just a bundle of algebras? There's a smooth sections of these bundles. I mean, but okay, so there's a little bit of. Okay, so this now computation shows that B is actually. So let me write the result because I mean it needs a little bit of checking. D is equal to D plus D star. This is a kind of important result. So again, you're going from direct sum of omega P of M, P bigger than or equal to 0 to itself. And of course, these operators we have met before. I mean, yeah, so that's That's what. Now, by the way, in this case, if you compute this squared, if you compute this squared, in this case, we computed, of course, this squared is equal to d plus d star squared. This is d star. I mean, okay, first of all, there's d squared plus d star plus d star d plus d star squared. But we saw that this is equal to 0. By the same token, this is also equal to 0. So you're left with two middle terms. So, and this is of course called Laplacian, right? So, I mean, then this operator, this squared in this case, is really honest to God Laplacian. Okay, so delta equal to, I mean, d squared, which is d star plus d star d. Now it goes from omega p to omega p for all p. Right? And this is the Hodge-Durand Laplacian. Okay. So now you may ask, hey, what happened to the other term in Buchner-Schneerowitz formula? Because here you just have this squared, and this squared comes out to be delta, which is, well, the thing is, this delta is not Nabla star Nabla. So that's a kind of, it's called Buchner Laplacian. Which is Nabla star Nabla. Well, Nabla is the Levi-Civita connection. So, you know, I mean, this is the Levi-Civita connection in this case. Okay, this Buchner Laplacian. So this is not this. This is the Hodge-Durand Laplacian. This is the Buchner Laplacian. So, I mean, if you want, you can write this squared then as Nabla star Nabla plus some term k. There is some left over. In this case, this k is related to Ricci curvature. So I will describe this a little later, but this is related to Ricci curvature. I mean, we have to go back to this definition of operator kappa k, and then we will extract Ricci from here. So, all right. So this squared. So yeah, this is Hodge-Durand. This is Buchner Laplacian, and the difference is Ricci. The difference between this and that is Ricci. So this is an important issue at some place, some point. At some point, this becomes an important issue. All right, so yeah, I mean, there is okay, I'm going to go now to also describe, we need a little more. So once you have one of these things, you can construct even more by just taking coefficients. So let me explain this. So this is called Dirac operators with coefficients. So again, but this is again generalized Dirac operators. Generalized Dirac operators
with coefficients in a vector bundle. So imagine S be a Clifford module. And let us imagine you have this vector bundle. I mean, E vector bundle. Oh, I use V for vector spaces. So let me just use E vector bundle over M. So we pick a connection plus Hermitian metric plus compatible connection. Compatible. Plus a compatible connection. So then we can define S tensor B, of course, has a tensor E, has a connection. And then this also becomes a Clifford module again. It's a new Clifford module. Clifford module. I mean, again, the reason is pure algebra, just because Clifford algebra acts on S, so it acts on this guy as well, right? By acting on this component, and it looks like it doesn't see, for the action, it looks like it doesn't see this part. But the connection on this one you introduce uses both connections, right? So then easy to see that this is also a Clifford module. It's a new Clifford module. So, and then we have got this Dirac operator dE. The Dirac operator of this is called Dirac operator with coefficients in E. With coefficients oh yes, so that's a way to extend the stock of your list of Dirac operators by adding more, by adding coefficients. Okay, now so to understand Dirac operator, I mean, to understand, yeah, indeed, Dirac operators, generalized Dirac operators, we have to understand Clifford modules. And to understand Clifford modules, we really have to understand the presentation theory of Clifford algebras. So this brings us back to the first lecture. So let me just recall. Now, so recall. Okay, so first of all, I mean, let n equal, just to be very specific, because the whole story breaks down in even and odd cases, and there are major differences between the two. So let n be equal to 2m be even. I mean, this is like dimension of n equal to n. So that's an even number. So recall that we basically showed that the complexified Clifford algebra of V, you see, this is isomorphic to endomorphisms of C to the power n, right? I mean, this guy, dimension of V
is what? Dimension of V is equal to 2n for any V, or dimension of V is equal to 2n. Oh, no, 2m, sorry. And just to check this, remember dimension, what is dimension of left-hand side? Dimension of left-hand side is 2 to the power 2m. And what is dimension of right-hand side? Dimension of right-hand side, well, oh, my God, 2 to the m is equal to 2 to the m squared, because this is a matrices, so this is same. I mean, this is, of course, it's just a simple check, but the proof of this was quite involved, right? That this is, and this is space, by the way, we denote it by delta, and this is called the space of spinors. Okay, so remember, dimension of my vector space or manifold is even, and the thing is, I mean, this isomorphism we obtain, there are different ways to establish this isomorphism. I think we just approached it directly, but anyhow, so we have this. Okay, but this was quite indirect. So, but the question is how to construct. So this is now the main question, how to construct an explicit isomorphism, right? Between the complexified Clifford algebra of V and this matrix algebra and the morphism of C to the power 2n. How can we write down a kind of explicit canonical isomorphism? I mean, the isomorphism that we obtain here depended on choice of bases. Now, one method to get this is to put a complex structure on V. So the idea is define J. So this is, remember, V is a real vector space. So V is like a tangent bundle at one point, right? Tangent space at one point. Real vector space of dimension 2m with a positive definite inner product. That is what V is. And now what is J? J from V to V. This is called a complex structure. This is again a linear algebra notion. So this is just R linear, first of all, plus J squared is equal to minus identity. Okay? So anytime you have a vector space with this R linear map such that J squared is equal to minus identity, this is called a complex structure on that vector space. Now you can do better than this. Of course, there are many such J's if V is even. Okay, I mean, one of the things is that this forces dimension of V to be even. So that's one thing. But another thing to know is that I just mentioned this, possible to choose J compatible with inner product on V. In the sense that not only J squared is equal to minus identity, but you can also satisfy this condition, Jx, Jy is equal to X and Y. I mean, that's definitely not obvious, right? I mean, you can see that if dimension of V is even, you can always find many such operators. That's trivial to do. That's not a problem. But then if you have an inner product, to make sure that what you chose is actually an orthogonal map, that needs a little bit of argument. So this is a nice exercise. Now, I'm not sure. Maybe you have to use averaging over a group, or maybe there is a quicker proof. One of these things will do. Anyhow, so this is a nice exercise. Okay, so now assume that you have chosen such a J. So then equip V with such J. First of all, this gives you a decomposition. Then J tensor 1, I mean from V tensor C to V tensor C. So you just complexify your vector space. It's a real vector space. And you just take identity map on this leg. And then you get this squared. It's still minus identity of V tensor C, right? So then you can decompose this into two pieces. And I mean, there are two eigenvalues of this operator, right? Plus I and minus I. So you can then write V tensor C as V10 direct sum V01. So these are two complex subspaces of the complexified vector space. I mean, this is I eigenspace. All of this is just linear algebra that can be done in second year even. So that's, and this is minus I eigenspace. Okay, and this is a notation you will see why we use this notation. This comes from complex analysis, by the way. So that's okay. So now what I'm going to argue is that actually let's call this P direct sum Q. I mean, it's kind of cumbersome to use this notation. I just used P direct sum Q. Now, the claim is that I mean, first of all, what is dimension of this guy over C? What is this dimension over C? Well, dimension of this guy over C is dimension of this guy over C divided by 2, right? So this is like dimension of V tensor C. Okay, so this is maybe offline now. I'm offline. So let's do this simple computation. Dimension of V tensor C over C, which is, of course, is still the same. It's 2m, right? Because dimension of this guy over R is 2m. So if you complexify, it's still 2m. And you divide, okay, so this is 2m. And if you divide it by 2, you get m. So the complex dimension, this is a complex vector space. The complex dimension of this guy is m. Is m, right? Good. So then I can take the exterior algebra of this guy. This is called, by the way, polarization of that complex vector space. So let delta be equal to the exterior algebra of P, which again, many times we did this. This is HP of, oh, P is bad, HK of P, K equal to 0 up to M. So dimension of this guy is 2 to the m. And that's what we want. It looks like that's, at least dimension-wise, this is good. Now the claim is that
the Clifford algebra acts on this guy. I mean, the complexified Clifford algebra CL of V acts on this guy, delta. Why? How does it act? It does act by similar to D plus D star, actually. So it acts really by basically exterior product and interior product. So let me just write it like this. So for any P, I mean, for any X belonging to a star of P, define, say, Px is equal to root 2 P veg X, and Qx is equal to root 2 Q interior product. Okay, so this is like differentiation. This is like the star. I mean the adjoint of differentiation. So here P belongs to P, and this Q belongs to Q. And remember, we just decomposed V tensor C. Remember, V tensor C is equal to P direct sum Q, right? Okay, so now, first of all, you have to check that when you act like this, if X is in vector star of P, which is delta, you again land in vector star of P, first of all. Okay. I mean, this is obvious because this is just exterior product. For this one, it's not obvious. You check that. And also, you have to check that P and Q satisfies Clifford algebra relations, so P and Q actions satisfy Clifford algebra relations. And going back to my first lecture, this by universal property of Clifford algebra gives us an action of Clifford algebra on this. Yeah. This gives us complexify, because this complexified Clifford algebra is like Clifford algebra of the complexification of V. So that's so this one V acts on which is delta. So because such a thing is unique, because this is a matrix algebra, so it has a unique irreducible representation, and its lowest dimension is this one. So that must be it. You haven't found anything, you can't find anything else except that. So this delta is the space of spinors. Now, one thing that's not clear is that we just used a suitable J, right? Of course, this choice of delta depends on choice of J. This delta depends on choice of J. I mean, J had two properties. Has to be a complex structure, has to be compatible with this inner product on V.
Now, the question is, if you want to globalize this go over manifolds, such J should exist in order to define a analog of spinors over manifolds. So the conclusion of this discussion is that to define the bundle of spinors over M, over a manifold M, which has dimension even and all these things, we need such a global J. Globally defined J. And such a globally defined J, its existence is not guaranteed. So the bad news or good news depends on your point of view. I don't think it's a bad news. It just did not exist in general. Not exist in general. So now I just give the last definition, which is the definition of a spin C manifold, and that's all we need so far from this discussion, is that a spin C manifold exactly is a manifold where such a minimal sort of, such an irreducible module exists in a coherent way. So let me define it now. And, spin C bundle. So let me erase this.
Could you maybe explain briefly why it does not exist in general?
Yeah, because you see, you make choices. When you define this J, you see, the point, exactly. The point is that if I give you a vector, so the point is really pure linear algebra. If I give you a vector space V of dimension even, and this inner product V, there is no canonical choice of J.
Oh.
Such that J squared is equal to minus identity and is compatible. There's no canonical J.
Mm.
There are many, but we don't know which one. So it's like axiom of choice.
Well, if you assume axiom of choice, you can pick one. But I think the thing is that you will not make it phi or something wise.
Yeah. Because we want to choose it in a continuous way. Yeah.
Yeah, I guess that's the problem.
Yeah, that's right. That's the problem. In a continuous, if you can do it in a continuous way, you will be able to do it in a smooth way also. That part is easy, but continuity is really, there is an obstruction. But the philosophy is very important here. The philosophy is that, I emphasize this from the beginning. If you cannot do a construction in linear algebra or algebra in a canonical way, there is no way that this exists on manifolds in general. You will face some obstructions, and actually obstructions are very, very interesting obstructions for existence of such thing. So we'll discuss that a little bit. Yeah, okay, so this was a good question. So now let me erase that. So now, so this is the definition, last one. Let dimension of M equal to 2M. And M be a Riemannian manifold. So a spin C bundle so the notation is the spin C, or sometimes we can just put spin C here. I don't know which one is the better one, but spin C bundle on M is a complex vector bundle S over M such that, well, I mean, this is a smoothly defined or continuous complex vector bundle such that for any x belonging to M as X is the reducible module, is, I mean, isomorphic to delta, which is the reducible, I mean, up to isomorphism, this is unique. This delta up to isomorphism is unique, and of course we are talking about up to isomorphism here. The reducible Cliff TMX module, and notice I'm clearly thinking this as an algebra, so I just say at that point there is this algebra, which is dimension 2 to the power 2m, and there's a unique module of dimension 2 to the m, and I want the fiber at that point to be that module. This was the module. So this is a very important definition. So I'm not defining spin bundle yet. I may not define it even because I don't need it.
Is it a Clifford algebra, a Clifford module bundle?
What's that?
Is it a Clifford module bundle?
This one?
Yeah.
Yeah, we want it to be also Clifford module bundle, but the other parts can be adjusted. The difficulty is really to have this moving. Yeah, it's a Clifford algebra, Clifford module bundle we want it. But point-wise, we want to be this irreducible one that's the minimal dimension.
Okay.
And so what does this mean? This is really a square root of an algebra, right? So this, remember, I mean, here, this delta, you can think of it as a square root of CL.
Oh, wow.
Delta is a square root of CL. I mean, this, of course, this equality, I mean, you have to understand it in a kind of imaginary way. What does this mean? This is an algebra, but this is just, you know, this part. So I mean, you make a kind of, I mean, this sort of a spinors is really like a square root of Clifford algebra. But, okay.
Well, I'm just thinking if this spin bundle would be kind of an analog of irreducible module of that thing.
Yes, exactly. That's the global analog of irreducible module for Clifford algebra bundle. Yes. Point-wise, fiber-wise, we want to maintain irreducibility, but globally we should have this continuous structure. Yes.
You would also have uniqueness in this case?
No. Yeah, that's an excellent question. No. When you globalize, you use uniqueness.
Okay.
So note, so this is an excellent point, note. This bundle S need not be unique.
Okay.
I mean, I have to give you examples. I mean, constructing any sort of example here takes a couple of hours to explain. I don't see any examples right away, but for example, on the case of Riemann surfaces, there are some examples.
Okay.
But the question is, are there finitely many over a given manifold? If there are things, I cannot say right now. If there are finitely many, I'm not sure. Some cases there are, but in general, I don't know the answer right now. But the thing is, definitely need not be unique. That's one thing, but now the question is, okay, show me one example of such things now. So what is an example of such things? So the question is, how to cook up an example of this? What are the examples? I mean, there is a very general class of examples, and that class is the class of complex manifolds. So the answer is So I don't get into that, but you can read up easily complex manifolds. I mean, complex manifolds are examples of spin C manifolds. I mean, they are spin C manifolds in the sense that there exists this bundle. So what is this bundle? Just let me quickly tell you. So first of all, what is a complex manifold? Okay, so what is a complex manifold really? I mean, you can define it basically in 2 lines. You can define a complex manifold in 2 lines. So let me tell you what, I can give you the first line, the second line, you can explain a little more, but let me just give you what is a complex manifold. So a complex manifold is a real manifold. So i.e., M is a real manifold plus this J that exists on the tangent bundle. So is an endomorphism of the tangent bundle such that J squared is equal to -1, right? J squared is equal to 1. And this field of, so we have globalized the idea of complex structure now. So this field of vector, I mean, this bundle maps, this is called an almost complex structure. So sorry, today there are many definitions, I'm sorry. Almost complex structures. Okay, so what is a complex manifold? Is a almost complex, it's a real manifold such that there exists an almost complex structure, but there is a second line of the definition is that this complex structure has to be integrable. So I don't get into that. But this almost complex structure is enough, I think. Because J has to be integrable. Yes, you can go online and read this. There is a definition of integrability. I don't want to define it, but anyhow, so it has to be integrable. So now, if you have such a thing, you can take S to be. So J gives you Tm tensor C, which is TMC. It's called complexified tangent bundle. We'll just do fiberwise as concept. You can write it as a piece, as sums of 2 pieces. This time it's very standard to use this notation. And then you can use, you can also decompose the dual space. So T star and tensor C, which is T star. And C, you just also write it as, again, as T star 1 0 x on T star 1 and then you have decomposed, and you just take this to be P, and you take wedge P to be your S. So this is your bundle of spinors. I mean, spinors in the sense of a spin C structures. Okay, so now what else we need? Okay, so yeah, I mean, this really gives you an example of spin C manifolds and spin C structures. So by the way, I mean, there is a notation here, C infinity of HP, because this is direct sum, so this is direct sums. So notation is, actually we have to use this one. So we call, somehow we just use this P and this Q, sorry. And this is P, this is Q, but duality, by duality, this should be Q, this should be. So anyhow, that doesn't matter. That's my definition of P. And if you take smooth sections, you just get the smooth sections of wedge P of T star 0, 1, which is, okay, so P and P is kind of HK maybe. Okay, now this is, we are there now because this is a very well-known object, omega 0K. So, okay, so 0K forms. I mean, formally, that's it. That's all you need to know. And this is your S. I mean, this is the infinity of S. And this is the bundle of spinors. So the point is that complex manifolds provide a great source of spin C manifolds with a canonical spin C structure, which is simply because you have a canonical decomposition of this complexified vector space given by the structure. So this is part of the structure of the complex manifold. And so now we are going to start talking next time on Wednesday. I think we are in good point. On Wednesday, we are going to start talking about index of these operators and see what we want to do. I highly recommend you read up a little bit about this thing so that just, yeah. Okay, so I'm going to stop the video and then ask questions. I mean, we can ask questions.